So we are on week number 8 now, which is getting pretty close to the end of this semester. And today we're going to be talking about mathematics for quantum. Now, you would be correct to say that, well, technically we've been learning mathematics for quantum pretty much this whole time. And you would be correct. So in fact, a lot of what we're going to be doing today is going to be review, but we're just going to be going over a lot of these concepts again to make sure that they're clear with everyone. And that everybody has the backing they need, especially before we go into the winter break and going into the second semester, when we'll start diving into some of the more complex topics. So as usual, let's take a quick look at the program for today. Pretty usual, we have our attendance quiz, pre-lab Zoom feedback. We'll have a couple of clarifications from last week's content. Then we'll go into this week's content on mathematics for quantum. And finally, at the end, we'll have our post-lab Zoom feedback as usual. Now, today's lab is going to be back to sort of the more normal labs that we're used to, where it's just me writing math on a tablet. So we took a bit of a detour for programming last week. This week, we're back to just mathematics, which is going to be a lot more similar to some of the previous labs. So let's do the attendance quiz. As usual, log on to Canvas, find the attendance quiz for lab number 2A. The password for tonight is 5430, which as always, you can find in the bottom right of the slides as well. So the two questions today, number one is how useful is your lab section? And number two, in general, how is the pacing of the lectures? So both of these are essentially feedback questions for us, especially as we start planning things for the second semester. Now, just a note here, we don't look, or like I don't, and the course administration staff, we don't look at your individual answers to these questions on Canvas. So please feel free to just be totally honest. We want an accurate picture of how useful you're finding the lab section, as well as how the pacing of the lectures is. So please don't feel obliged to say that everything is perfect because you think we'll be looking at them. We will not be looking at these answers individually. We just want to see the aggregate data to see how things are going. And final point, as always, the quiz is not graded. And so clearly you're not going to get a better grade or anything for saying that we're doing a better job. Once again, the password is 5430. I'll give about 30 seconds here for everybody to fill out the attendance quiz, and then we will get going with the lab. Okay, so let's get started then. First up, as always, if I can get my tablet to work, the pre-lab Zoom feedback. So you should see a poll popping up on your screen any minute now. Please let me know how well you understood this week's content. So as usual, scale of 1 to 5, 5 being it was perfect, everything makes total sense, 1 means that nothing makes sense. And if you're somewhere in between, let me know. Okay. Wow, this is almost a perfect normal distribution, about 3. Interesting. All right. Cool. So why don't we get started? First of all, before this week's content, let's talk about some of last week's content. So starting off, this is, I guess, just a more general question, which we probably should have done a better job answering last week, but we'll answer it retroactively because I think it is an important point, which is why are we learning Python? Does a quantum computer understand Python, or is there some other connection? Now, I like to think of this in terms of a kind of like an analogy, or I guess you could just say it's a higher level picture. So if you have a programmer, so let's just say it's me, and you want to communicate with a quantum computer, the so-called raw inputs to a quantum computer, much like any circuit, are just going to be electrical signals or magnetic signals, that kind of thing. So like, sending electrons down a piece of wire, that's the raw input to a quantum computer. Now, if I'm a programmer and I want to tell the computer what to do, I don't want to be down so low level that I have to be telling it which individual wires to be sending electrons on and when. That would become super complicated super quickly. And so in computer science, as well as quantum computing, we have layers of abstraction. We have some code that sits way down close to the quantum computer and does that translation to individual electrons on the wires. But then we also have code that sits up closer to the programmer, which is going to look more similar to the gates, matrices, and vectors that we've studied so far. So what ends up happening in real life when you program a quantum computer, you're sitting over here as the programmer, you write some code, and we'll learn how to write this code in Python in the second semester, but suffice it to say that the code looks very similar to what you've seen before. That code, though, is then interpreted. So there's this layer in here, and we're going to be using IBM's software. So this part right here for us is effectively going to be IBM. You pass your code into IBM, and they have some software that's going to go and translate your Python code to the electrical signals that ultimately power the quantum computer. The final step, of course, is you have to get some kind of feedback. And so the quantum computer's output is also going to be some electrical signals, and that has to be passed through a translation layer before it gets sent back to you in code. So all of these sort of boxes in between, the things that mediate between you, the programmer, and the quantum computer, are these pieces of software that are written by IBM. There's other companies that do it as well. But this is kind of like the interface that we're going to use in the second semester to actually program for a quantum computer. Now, as a more general comment, this might not be as applicable for this course, but if you take a step back, these are not the only levels of abstraction that we sometimes have. So this is the whole system we just talked about on the previous slide. You might also have other layers of abstraction. So here we might have a chemist, for example. So maybe I'm the programmer, but there's now a chemist who wants to do a chemistry simulation on the quantum computer. So the job of the programmer in this case is to effectively write a translation layer that's going to translate from the language of chemistry into the language of code. And then that code is going to be interpreted by IBM to electrical signals. And then eventually those electrical signals get run on the quantum computer. And then you get your output fed back. So there is going to be more, obviously, about this in semester 2. But the real point we wanted to lay out here is when we study Python, we're kind of looking at this level right here, the code that you're writing as a programmer. That is only really one small part of this whole system, though. It's enough to start using a quantum computer, but these are some of the other areas that you might look at if you chose to study quantum computing in the future. You might learn more about the electrical signals, you might learn more about some other branch of science that requires quantum computing, all that kind of stuff. There's a lot of other pieces to this system besides just the code. So that's all we had from last week. Does anybody have questions from last week's content, just in the chat? I'd be happy to try and answer those now. Yes, the IBM quantum experience. It's very grandiose, don't you think? So any questions from last week? Going once, going twice. Okay, cool. Let's talk about our agenda for today then. Now, as I mentioned before, a lot of this is going to be review, but we're just going to go over it all again because they are all very important concepts. I believe now there actually is one piece that's going to be new right at the end, but it's a relatively small part of the lab, so the majority of this is going to be review. We're going to start off with some of the linear algebra that we learned. So superpositions, normalization, inner products, Bra-Ket notation, all that kind of stuff. Then we will review one of the more recent labs, which was about quantum gates. So that's when we talked about matrix multiplication, matrices, how that related to quantum gates, and how to apply a quantum gate to a quantum state. And then finally, we'll talk about measurements. So measurement is something that happens in classical computers as well, but in the quantum world, it's a little bit more complicated and turns out to play an important role in quantum computing. So we'll do a bit of an introduction to that right at the end. So before we dive into any of those specifics, let's just take a step back here to, again, contextualize what we're learning and see where we are in the whole system. So here we have a circuit diagram of a classical computer. Now, this is obviously quite complicated. I don't expect you to know what this does, but you should know what all of these pieces are. So if we just look at a very small part of this circuit, for example, this piece here on the left, you should recognize that that right there is a NOT gate. This here is a NAND gate, and then we have an XOR gate. And if I gave you all of the inputs to these gates, you should be able to figure out what that eventual output is going to be. And so when you're designing a whole computer, obviously there's much more to it than just the part I've highlighted here, but all of these pieces just use the same basic building blocks that we already introduced. It's just you combine them in more interesting and complicated ways. So let's zoom in on this one part of the circuit. Here we've just kind of flipped onto our side. So I'll just flash back and forth for a sec. We're taking this whole thing and flipping it 90 degrees. So our inputs up top are now inputs on the left. So we have our two inputs. Doesn't matter what they're called, but they're binary. They're either 1 or 0. Then we have the main part of the circuit, which in this case we'll just call the classical computer itself. And then finally, at the end, once we've applied all of our gates, we have some kind of measurement. So in real life, all of these lines represent wires. 1s and 0s represent different voltage levels. And so at the end, we have to have some kind of instrument that's going to tell us whether there is a high voltage on the wire or a low voltage on the wire. And that tells you whether it's a 1 or a 0 in binary. So the overall flow here for using a classical computer is you're going to send input bits into the computer, it does stuff to them, and then you measure the output bits. Let's look at the same thing for a quantum computer. Here we again have a quantum circuit this time. So it looks a little bit different. And perhaps here you might not know exactly what's going on all of the time. But the basic idea is the same. Each of the horizontal lines represents a wire or some kind of medium that can carry a qubit instead of just a bit. And all of these rectangles, we know that these are H gates, and all of these other pieces here are also different kinds of gates. So again, we can go ahead and zoom in on just the top part of this circuit. We start off with the inputs on the left. We feed them into this quantum computer, which is just a whole bunch of different gates. And then at the end, we again need to measure the output. In this case, however, because we are using a quantum computer instead of a classical computer, the measurement, as I said before, is a bit different because now we can have superpositions of 1s and 0s. So we'll talk at the end of this lab about what measurement looks like. But for now, we're actually going to take this sequentially. We're going to start off talking about the inputs, then we'll talk about the quantum computer itself, and then as I said at the end, we'll talk about measurement. So to begin, the inputs. Let's do a quick review of bra-ket notation. So remember, bra-ket notation is just an alternate way of drawing vectors. So when we first introduced vectors to you, we drew them as letters with a little arrow over top of them. That's totally valid, but it just so happens that in quantum computing, your vectors are represented with kets instead. And these are just different symbols that mean the exact same thing. So we define the 0 ket as just 1, 0. We define the 1 ket as 0, 1. So these are things that you should just try and memorize. They come up all the time. And then we also had the sort of these things flipped around. We had bras. So when you take the conjugate transpose of any of these vectors, you end up with bra vectors or row vectors. So here 0 conjugate transpose, remember that's what this dagger means, conjugate transpose, turns into 0 flipped, which in this case is just 1, 0 as a row vector instead of a column vector. Then we have the same thing for 1. Now, just a reminder for how we do this. So this 0 conjugate transpose thing here, the easiest way to remember what conjugate transpose does is to just try and remember that word, because it says exactly what it's doing. First, you take the conjugate, which we denote by this bar over the vector, and then you take the transpose. That is just by definition what it means. So here our numbers are 1, 0, and then we're going to take the conjugate of both of these, transpose. Now 1 and 0 are both real, so the conjugate doesn't do anything to them. This is just 1, 0 transpose. And then we do the transpose, which turns columns into row vectors and row vectors into column vectors, and we get that as our final answer. We also learned about the inner product. So the inner product was just an operation on two vectors that we defined. And we found out that in linear algebra, you can write this as, for example, v comma w, to mean the inner product. In the symbols bras and kets, it's pretty much the same thing. It's just instead of a comma in the middle, you draw a straight line down the middle. So let's just do a quick practice to remind ourselves how this works. We'll compute the inner product of 0 with itself. So as a quick reminder, the best way to do inner product, in my opinion, is to just use the formula. There's a formula that's going to always give you the right answer in 2 dimensions. That formula was this. So we learned this a couple of labs ago. The inner product of v and w is v1 conjugate w1 plus v2 conjugate w2. So I'll go ahead and calculate this. The inner product of 0 with itself. Now, I will note this is the inner product of ket 0 with itself. That's not actually the number 0. So just remember that the vector and the number are 2 different things. In order to compute this, we'll just go ahead and apply our formula. So remember that ket 0 from the previous slide was just 1, 0. So v1 and w1 are both going to be 1, and then v2 and w2 are both going to be 0. So I'll go ahead, plug in this formula. We get 1 times 1 plus 0 times 0. And that, of course, is just going to be 1. So the inner product of these 2 vectors is 1. Let's give everyone else here a chance to practice this. So the question for you now is to compute for yourself what the inner product of the 0 and 1 vectors are. So as a quick reminder, the 0 vector is defined as 1, 0, and the 1 vector is defined as 0, 1. So I will give everybody here a chance to give this a try on their own, and I'll put up a poll on the screen where you can enter your answer when you're done. And just as a quick reminder, I did put the formula for inner product there in the bottom left corner of the screen. So I'll give a bit of time here and just wait until the majority of you have entered in your answer, and then I will quickly go over it myself before we move on. In the meantime, if anybody has questions about the content so far, feel free to throw those in the chat. Okay, so I'm going to go ahead and start working on this. Don't worry if you're still doing it. You can just keep on going and you'll probably finish before I get there. So the inner product of 0 and 1. Now I'm going to use the formula in the bottom left here. And as usual with these formulas, I like to label exactly what my variables are. So in this case, the 0 vector is going to be v. And so v1 is going to be up top here, and v2 is on the bottom. Then that means that w must be my other vector. So we have w1 and w2. Now, everything here is real numbers, so the complex conjugates don't do anything. So I will just use this formula to compute the inner product of 0 and 1. So we have v1 times w1, that's going to be 1 times 0, plus v2 times w2, it's going to be 0 times 1. And that, of course, is just 0. So the correct answer here should have been 0 as the inner product. Now, as a brief note on this, there is an alternate way of doing this type of question. And I just want to bring it up. Using this formula is totally fine. It's always going to get you the right answer. But if you are curious, there's another way of seeing it. So if you notice, one thing about this 0, 1, the way we've written it, it looks very similar, almost identical, to if you just had a bra vector right next to a ket vector. The only difference is that we kind of like squish those two lines together into a single line. And indeed, this is actually equivalent to the inner product. There's a reason we write it that way. These two things are equal. So another way you can compute this, if you look up here, 0, 1, we can interpret this as bra 0 ket 1, which by the definition of a bra vector is just the conjugate transpose of ket 0. We already computed what that was on the previous slide, and so you end up with this expression. And then the way that you multiply these is you basically go from left to right on the row vector and top to bottom on the column vector, multiplying a pair and then adding them together. So here we would get 1 times 0 is 0, plus, then we go right 1, down 1, 0 times 1, again 0, so the whole thing is 0. Again, you don't need to do it this way. I find in particular, remembering how to do this multiplication might not be the most intuitive thing. But again, you can use this method, you can use the formula method, both of them work just the same. Now, when we originally learned about the inner product, there were a lot of questions about what exactly the inner product was. What is the meaning of the inner product? And the brief answer that we sort of gave back then was that it corresponded to the angle between two vectors. So remember how we talked about comparing two vectors? We said you could compare the lengths of two vectors. You could also compare the angles between them. Inner product was a way to compare the two angles. So as an example, let's say that this is a map of the area where I live. It's not actually, but let's say it was. And let's say that my house was right there in the middle. Now, suppose there are two grocery stores located here. We could draw these as vectors. So if I wanted to go to grocery 1, I would have to walk somehow along this arrow to get from my home to grocery 1. Now, the inner product in this case is going to correspond to this angle here, the angle between the two vectors. Now, the reason that I say it corresponds to this angle instead of it is exactly equal to this angle, it's not actually exactly equal, but it is related. We're not going to go into more detail than that, but we're basically just saying that inner product is a way of measuring the angle between two vectors, even though it doesn't exactly give you the angle value. It corresponds to it. So I know that's kind of hand-wavy, but this is just a reminder of why we study inner product. It's basically used whenever you want to compare the angles between two vectors. So on the topic of qubits and bras and kets and stuff, we learned that qubits could be in superpositions. And what that meant in the language of Bras and Ketz was that you had some combination of the 0 and 1 vectors. So for example, here we have some coefficient alpha and some other coefficient beta. Now, just as an example, you could plug in actual values for alpha and beta. So here we have the imaginary value I. Alpha and beta can be complex or real or imaginary, it doesn't matter. And in this case, your total vector for psi would be equal to I2. Now, for a quick reminder on how you get this, well, we have that psi is equal to I0 plus 2 times ket1. So this, in a question on a homework or something, this would just be given to you by definition. It would say something like, suppose psi is equal to this, blah, 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 do something. So from here, I'm just going to substitute in the definitions of 0 and 1. Then if I move these constants inside the vectors, we'll get I0 plus 0, 2. And then if you remember how to do vector addition, we just add all the top elements, add all the bottom elements, and your final answer is I2, which is what we have right there. So usually in quantum computing, we will write things in this way. I guess that's just convention. But the important thing is to not be too freaked out by that. It's really just another way of writing a vector, which we've seen many times by now. Now, this state here, this ket psi, is almost a proper superposition, but there is one thing missing here, which you might have noticed if you have a really good memory, and that is that we need to normalize it. So let's do a quick review of what normalization is. We'll keep the same example. So psi is equal to I times ket0 plus 2 times ket1. And now we want to find the normalized form of ket psi. Again, we had a formula for this, so I'll bring that back into the bottom left. The normalized version of a vector was sometimes denoted as the u hat. So if it was originally called u arrow, it might now be called u hat. And the way we calculated it was we took our original vector and we divided by the norm of that vector. So let's go ahead and compute the normalized form of ket psi. So I'm just going to call this psi norm. So this is going to be equal to, we'll use this definition. So I know that sometimes here we're using the ket notation, here we're using arrow notation, but again, they mean the same thing. So here we'll have ket psi on top divided by the magnitude of ket psi. Okay, now to do this, we have to compute the magnitude. So let's go ahead and do that. Remember that the definition for this was the square root of the two elements squared. There is a bit of a catch here. Whenever you do the norm with a vector of complex numbers, you don't just take the square, you have to take the modulus squared. So we would write that like this. So modulus I squared plus modulus 2 squared. So if you remember back to the definition of modulus, for a complex number, it's just looking at the distance away from the origin on the complex plane. So I is just going to be a distance 1, and 2 is of course just a distance 2. We take the square of that, and we get that it's root 5. Okay, then we go back, we solve our original question up here. Psi divided by root 5 is just going to be another vector, but now everything is divided by root 5. So as a general comment, when we start doing more math with quantum computing, it's a good idea to always make sure that your vectors are normalized. So if you have a qubit state that is not normalized, your answers will probably be wrong. And this is actually a really common trick question that you might see in this week's homework, I'm not sure, or homework in the second semester, where the question will start off by saying, hey, ket psi is equal to this thing. Go off and do a calculation. But your first step should always be to normalize. So it can be kind of a gotcha where it's like, oh, you forgot to normalize, then your answer is wrong. You always just need to remember to normalize your kets. one other quick note I will make here. This definition of norm using like the modulus squared, this is something that people forget all the time. So notice if I had not taken the modulus, which would be incorrect, I would have gotten something like this. We would have had I squared plus 2 squared. Now remember that the I squared, by definition, that's -1. So we would have ended up with -1 plus 4, which would have been √3. Obviously not the same thing as √5. So whenever you are doing norms of, or sorry, whenever you're doing the magnitude of a complex vector, always make sure you remember to take that modulus of any complex numbers. Otherwise, you will get the wrong answer. Okay, cool. So let's do one other quick example with inner product. This time we'll do an inner product of 2 superposition states. So here, I'm going to go ahead and write out these 2 states. So in a question, you would probably be given these definitions, but honestly, it's a good idea to just memorize ket plus and ket minus. You'll see these 2 things popping up all the time. So the recommended way of doing this question is you first write your kets in terms of column vectors. So instead of writing it in this like coefficient 0 plus coefficient 1 form, just write it as a column vector. And then you can go ahead and apply the same formula for inner product that we saw before. So in this case, our V is plus. So this up here is V1, this down here is V2. Then we have W1, and W2. Just remember to include these 1 over √2s as well. So the inner product of plus minus, oops, if I can draw correctly, is equal to, so V1 is going to be 1 over √2. Again, there's no complex numbers here, so I don't have to worry about the conjugate. W1 is also 1 over √2. Plus, now we take V2, 1 over √2. And W2 is going to be minus 1 over √2. So I'll multiply all of this out. We get 1 over 2 minus 1 over 2. And that is, of course, just 0. So it turns out, much like the example that, that you tried on the Zoom poll, this one also has an inner product of 0. So we went over Bra-Ket notation. We talked about superposition states. We talked about inner products and normalization. All of those are technically review, but I know that it's a lot of content. So does anybody have questions about what we went over so far? Sure, so I'll go back to the last slide and then I'll ask this last question. Does the modulus kind of act as absolute value? Yes, it does. So in fact, for real numbers, the modulus is exactly equal to the absolute value. The only place where a different definition comes in is when you're dealing with complex numbers. So for example, when I had earlier, I had the modulus of 2 being squared. That is the exact same as just taking the absolute value of 2. Now, the place where you have to remember the technical definition, which involves, remember, the square root of the real part squared and the imaginary part squared, that you need whenever it's a complex number. Can you show a quick complex number example for normalizing and inner product? Sure. So actually, on the inner product example, well, so here's an example of normalizing with a complex number. Inner product, I guess I didn't do. So yeah, I'll go and try an inner product example. So let's try with that same ket psi that we had before. And so if you remember, this one was I over √5. Once we normalized it, ket 0 plus 2 over √5, ket 1. And let's say that you were asked to take the inner product of psi and plus, just to make it kind of complicated. Okay, so the first step in this is to write everything as column vectors. That's always going to be your first step. So remember, writing it this way is kind of the quantum computing way of writing it, but when you're about to do some math, it's better to write it as a column vector first. So remember, this is just a shorthand notation. I over root 5 goes on top, and 2 over root 5 goes on the bottom. No funny business here. You're literally just copying that one up there, and that one goes down there. So far, so good. Now for plus, the definition of that is 1 over root 2, 0, plus 1 over root 2, 1. And remember, if you don't memorize these kinds of things, you can always go back to the lab slides or the lecture slides, and we'll have these definitions. So I'll write this as a column vector, again, just copying these elements to the top and bottom. Okay. Now, to do the inner product, I'll quickly write that formula we had. VW equals V1 conjugate W1 plus V2 conjugate W2, something like that. And so as usual, I'm going to go ahead and label my V's and W's. So V is the thing that's on the left, which here is psi. So we have V1, V2. And then W is the thing on the right. So we have W1, W2. And now with all of that, I am ready to apply the formula. So let's start off. Here we do have complex numbers. We have the I up here. So we have to be careful about conjugates. In fact, our first number here is V1 conjugate. So that is I over root 5 conjugate times W1 is 1 over root 2 plus V2 conjugate 2 over root 5 conjugate times 1 over root 2. Okay, so let's go ahead and calculate these. Remember that the conjugate just flips the sign of anything that's imaginary. So here we have an I, that's going to turn into a negative I over root 5, 1 over root 2, plus here, same deal, conjugate flips the sign of anything imaginary, but here we don't have any i's, so it actually doesn't change it. This is still just 2 over root 5 and 1 over root 2. So if I go ahead and compute these, we're going to get what? Negative I over root 10 plus 2 over root 10. And that would be our final answer. So it is totally okay, and sometimes you do get a complex inner product. So in this case, we got a complex number as our answer. And that would be your final answer. Hopefully that helped. And if it still didn't quite make sense, definitely feel free to go back and watch the recording again. So we would always need to apply conjugate if there's an imaginary number. Yes. So the inner product definition always includes conjugate in it. It's just sometimes when I've been doing problems, I drop the conjugate when there's only real numbers, because I know conjugate operating on real numbers doesn't do anything. So you can just forget about it. If you do have complex numbers though, you always need to include the conjugate. Okay, so let's charge ahead. We spent the last few minutes talking about the inputs to our circuit. So those are quantum states, they're represented as vectors. The next piece to talk about is the middle here, the quantum computer itself. And if you think back a couple labs ago, this is represented by matrices and quantum gates. Now, there are a whole bunch of quantum gates. For example, now some of these, I'll say it right now, some of these we have mentioned before, some of them we have not, so don't worry if some of this doesn't look familiar. One of them is called the Z gate, and the Z gate is, I mean, in a circuit, you just write it as a box with a Z inside. The matrix looks like that. This is just something that you basically have to memorize. We also have an X gate. So same idea, you just put the letter inside the box, and then you have this matrix representation. We also have something called the Y gate, which I don't think we've seen before, but it looks like this. So now we have some imaginary numbers in there. No big deal, as long as you remember your complex number arithmetic. And then we have a couple of other ones over here that we may or may not have seen before. This one's called a rotation gate, and it has a complex number down here, which remember has to do with Euler's formula. It's basically a point on the unit circle. Here we have something called the root naught gate, which has this funny symbol, looks like that. The Hadamard gate, which we saw before, the H gate. So these are all just different examples of quantum gates. And you don't have to memorize these. If by chance some of them came up on an assignment, you could just go back and look at this slide. But the real point here is to show that quantum gates are always represented by a matrix. So whenever you see a quantum circuit drawing, you can always go and look up the matrices for each individual gate. So just to push this point, you do not have to memorize these. In fact, please don't try and memorize these. There are quite literally an infinite number of gates out there. So you just kind of look them up when you need them. Let's talk a little bit about how you apply a gate to a qubit. So let's use the same state we had before, this ket psi. So this one has an imaginary number in it, so we're gonna have to be careful with that. And we've already normalized it. So remember, when we first saw this, it was just I0 plus 2 ket 1. Here we've already normalized it. So suppose this ket psi is the state that started off on the left-hand side of our circuit. And then we want to pass it through a Z gate first. So we apply a Z gate. And then after that, we apply an H gate. And then we want to find the final result. There's a few steps. Step number one, kind of like before, is to find the column vector form of psi. So this is pretty straightforward. Again, this notation here is just a fancy way of writing two rows. So our vector psi is just equal to, there's no funny business here, no conjugates, no flipping, nothing. You just copy this, put it up top, and then copy this, put it on the bottom. That is the column vector form of psi. And with that, step one is complete. So step two now is to start multiplying for every gate that we're applying. So remember when we first learned about matrices, we learned that applying a gate to a quantum state is equivalent to multiplying the column vector by the matrix. So here we just computed before that the column vector form of this was I over root 5, 2 over root 5, like that. Now, to figure out what happens after the first Z gate, we just have to do matrix multiplication. So we're going to have Z times psi, which is equal to, now I'll plug in the definition of the Z gate. Again, don't worry if you don't remember it. You can always go back to the previous slide. And then I'll put the column vector form of our state psi. Just like that. So now you would have to go back and remind yourself how to do matrix multiplication. There is a formula for this. So I didn't write down the formula just because it's a bit long, but the formula involves 4 elements inside the matrix, 2 elements inside the vector. This formula has no conjugates or anything like that, but there is another way to see it. And the way to see it is this. We know that we're going to get a vector coming out the other end of this. To calculate the first row of this vector, we're going to look at the first row of this matrix and multiply the elements pairwise with our vector. So what does that mean? Well, looking at the first row here, I am going to take 1 times I over root 5, and then plus 0 times 2 over root 5. And that gives me the first row of my result. Now, to do the second row of my result, I'm still going to look at this vector, but now I look at the second row of my matrix. Same deal, 0 times I over root 5 plus -1 times 2 over root 5. So if you need a refresher on that, I would encourage you to go back and look at the lab on matrices. Then I can just work out what this should be. This one up here goes to 0. This one down here goes to 0. And so we get I over root 5 on top and minus 2 over root 5 on the bottom. So this is another quantum state represented by a column vector. And essentially, this is the state you get when you apply the z gate to ket psi. So we're about halfway through our problem. Remember, we were originally asked to apply a z gate, and then you also have to apply an h gate. So that's going to be step number 3. So in step number 3, you're going to multiply the matrix of the h gate by the vector we just had on the previous screen. So remember, the vector we had on the previous screen was this. Actually, I should have written this off to the side. The vector we had on the previous screen was this. And now what you're being asked to do is multiply the matrix of the h gate, which, as a reminder, looks like this. Again, don't worry about memorizing, just go and look it up. Multiply that matrix by this vector, you should get another vector. And the question now is what that vector is. So this is a bit of a longer question, so I'll give a bit more time to do it. But once you have your answer, go ahead and fill it in on the Zoom poll. And once the majority of people have entered in their answers, then I will go ahead and do it myself as well to show what the answer is. Okay, so as people are still working away on this question, I'm going to get started. So this process works the same way as what was on the previous slide, except now we are going to have a different matrix and a different vector. So just like before, to find the first row of my answer, I'm going to look at the first row of my matrix and my vector, and I'm going to multiply them pairwise. So we have 1 times I over root 5 plus 1 times negative 2 over root 5. Okay, now to do the second row, I'm going to look at the second row of my matrix right here. 1 times I over root 5 plus, now we have a negative 1 times negative 2 over root 5. And then remember, we also had this constant out front. So we'll just multiply the whole thing by 1 over root 2. And if we work this out, what we're going to get is, so we have an I minus 2 up here. I minus 2 over root 5. Then down here, we have an I, negative times negative is a positive. So this is an I plus 2 over root 5 times 1 over root 2. And then we can just bring the 1 over root 2 inside. So our final answer is I minus 2 over root 10, and then I plus 2 over root 10. So that should have been the correct answer to the Zoom poll. Okay, so let's do a quick review of what we've done so far and also check our answer. So here's what we should have gotten. Remember that we started off, we were given this state. We wrote it as a column vector, which looked like that. First, we applied a Z gate, and the output was I over root 5 minus 2 over root 5, which is kind of like an intermediary state. And then we went ahead and applied the H gate to that. And on the previous slide, we should have gotten that as our final answer. So this is just a diagram of what the circuit would look like. You have your Z gate followed by your H gate, and then you have your input and output quantum states on the two sides. So does anybody have questions about matrix multiplication, representing gates as matrices, applying multiple gates to a quantum state, any of that kind of thing? Feel free to throw questions in the chat. Okay, so seeing no questions, I will move on to the last section on measurement. So again, just to contextualize everything, we have now looked at our input states. We've looked at what goes on in the middle, how you compute gates being applied to quantum states. The last thing to look at, which we actually have not seen before in labs, is the measurement, how we actually determine the output of our computation. Now, here it's helpful to compare and contrast with classical computing. In classical computing, if you have an output bit of 1 and you measure it, you're always going to get a result of 1. That seems pretty straightforward. Now, you could also have an output of 0. Again, you measure it and you get a result of 0. And at this point, these words output and result kind of seem like, like pointless distinctions. And indeed, in quantum computing, if you had a qubit state 1, you measured it, you're always going to get 1. And if you had a qubit state 0, you measure it, you're always going to get 0. The interesting thing comes when you have a superposition of 0 and 1. Now, it's helpful to kind of visualize this as a big dial. So it's kind of like, or not a dial, but like a gauge. So for example, you could think of this like the gasoline on your car, right? On one side, you've got your empty. On one side, you've got your full. And then in the quantum world, your actual quantum state, which is this arrow, it can be anywhere in between. You could have a 50-50 split. You could have a 25-75 split. You could have a 1/3, 2/3 split. It doesn't matter. And sometimes it's helpful to just look at this diagram for an idea of which state you're closest to. Now, when we actually measure in the quantum world, we're always going to get a 0 or a 1. But when your state is in a superposition, it has a chance of going to either 0 or 1. In this example, your state is more likely to be measured as a 1 because it's closer to that side. but it still could be measured as a 0. There's a chance of that. If you look at this diagram, same idea. Now there's a higher chance that you're measured as a 0, but there is still a chance that you're measured as a 1. So this is all very abstract. What does it actually look like in mathematics? Let's do a quick example. So here we have an output state. So suppose we essentially did step 1, step 2, step 3, just like we did previously. And we ended up with a final state that was this. So 0.8 ket 0 plus 0.6 ket 1, which, as a reminder, is just this column vector. Now, how do we figure out what the result is? It turns out in quantum computing, there is just kind of a rule for this. The probability of a result of 0 is going to be 0.8 squared, which is 0.64. And the probability of 1 is going to be 0.6 squared, which is 0.36. And it should come as no surprise that these two things add to 1. Because of course, with probabilities, they always have to add up to 1. So all we've done here is we've taken the coefficient in front of 0, square it to get the probability of 0, and the coefficient in front of 1, square it to get the probability of 1. Then our result is going to be either 0 or 1. The result itself after measurement cannot be a superposition. So in general, the way this looks, if you have a general state, alpha, beta, these could be complex numbers, remember? So again, we get this technicality that you have to take the modulus squared. So it's not just the square. If it's a complex number, you have to take the modulus squared. And that will give you the probability of the result being 0 or the result being 1. So there are several, I guess, unanswered questions about measurement. You could ask any of these. You could ask, why do we only measure for a 0 or a 1? Can we actually do a different kind of measurement? Could we measure for something besides a 0 or a 1? You could also ask, what is the quantum state right after measurement? We haven't talked about that. We just said you could translate an output quantum state to a result, but we never said what the quantum state is after you've measured it. And then finally, what would we get if we measured the same qubit twice? Would it be a random probability event each time? Or would you always get the same answer if it was the same qubit? Now, all of these are very good questions and have well-defined answers, and we will address all of them coming up in the next semester. So let's do a very quick summary from all the stuff we talked about today. Bra-ket notation is how we represent quantum states. A ket is a column vector, bra is a row vector, and then the inner product is a bra-ket, which is literally bra symbol followed by a ket. In the second section, we talked about how quantum gates are represented by matrices. And so applying quantum gates to qubits is multiplying a gate matrix by a qubit column vector. And finally, we touched very briefly on measurement, that the result of measuring a qubit state is a probabilistic event. It's random. And so the way we calculate these probabilities is using the modulus squared of these alpha and beta values. So does anybody have final questions? Oh, actually, I just saw someone sent a question. So I'll answer that in a sec, but feel free to send any other questions you might have in the chat. So if we measured the qubit in between the Z and H gate from the earlier question, it would change the outcome, right? Yes, that is correct, but let's be a little bit careful about whether we mean the output or the result. So it will change the probability distribution of the results. So you might have a different chance of measuring one thing than another, but there is still a chance, a probabilistic event, that you could get the same result. So this is something we'll talk about more in the second semester, but usually when you measure a quantum state, you cannot be 100% sure of what it was before the measurement. So in this case, it would change the probabilities. Your answer would be different, but there is a probability that the results would still actually match. Hopefully, and actually, if you don't fully understand that, I know I'm kind of hand waving. We will talk about it a lot more in the second semester, so don't worry too much about that. Does anybody else have questions about any of the content we've covered in lab so far? Someone just asked if I have any recommended books for beginners. Hopefully watching all of the labs and lectures again will be enough to get the content for this course. If you are still struggling, I would personally just recommend you to post on Piazza. I'm sure you could find maybe like some Khan Academy videos or something like that that teach the linear algebra concepts. It might be a bit more difficult to find resources for the quantum computing concepts. So for all the quantum computing stuff, I think watching our lectures would be a good idea. Someone also just said in the chat that IBM has an online textbook, which might be a good resource. So yeah, those are both good suggestions. All right, I know we are a little bit over time, so we'll head into the post-lab Zoom feedback, and I will quickly launch that poll. So as usual, scale of 1 to 5, how comfortable do you feel with the content now that we've sort of spent a bit of time reviewing everything? The other thing I'll mention actually in response to that question about books for beginners, we are putting together a resource list right now as well of sort of free online resources that you can check out if you want to learn more about any of these topics. I think we're supposed to have it out by the winter break. Don't quote me on that. But at some point in the near future, we'll be sending out sort of a resource list that should help with some of these questions as well. You're welcome. All right, so with that, I will end off the required content. So everything I've set up till now should be enough to do the homework. If you want to head out for tonight, no hard feelings. Good luck on the homework, and we'll see you next week. If you want to keep learning for a few more minutes, I'm now going to move on to the optional content, which again is 100% optional. Don't feel obliged to stay if you have other places to be tonight. So I'm going to give my voice a rest for about 30 seconds. Let people head out if they need to, but if you do want to stick around, I will resume with the optional content in about 30 seconds. Okay, let's get started with the optional content, which is actually not too much this week. It's basically combining some of the things we have seen before. Now, somewhat inadvertently, I guess, I sort of did an example of this before when somebody asked the question, but here I guess we'll do just another practice problem to show how you calculate the inner product of a superposition state. So, as always, the way to do this, the first step is always to start off with column vectors. In this case, we have two states that we care about. First one is ket 0. So ket 0 is just by definition 1, 0 as a column. And then we also have this ket psi thing, which is written in the quantum computing notation. We're going to write it in column vector form. So it's 3i over 5 and minus 4 over 5. Just like that. Now I'll bring back our formula for calculating inner product. So always feel free to look that up whenever you need to do an inner product question. And I'll go ahead and label our variables here. So 0 is the one on the left, which is v. So here we have v1 and v2. And then w is ket psi. So here we have w1, w2. Now, to compute the inner product, we just apply our formula. So to start off, we have v1 conjugate w1. So let's look at v1. conjugate means you flip the sign of any imaginary parts. There's no imaginary parts here, it's just real. So the conjugate is just the same thing. 1, W1, there's no conjugate, so we don't change it at all. It's just 3i over 5. Then we plus V2 conjugate. So again, 0 has no imaginary part, so we don't do anything for the conjugate. Then W2 is going to be minus 4 over 5. Now at this point, you just have to do the math. This whole term goes to 0, and so we're left over with 3i over 5. And that's the final answer here. Again, it's okay to end up with a complex number as the result of your inner product calculation. Sometimes they do pop up. So this would be our final answer here. Now, let's bring in a little bit of what we learned right at the end about measuring. So in this case, if I asked you the probability of measuring 0, remember that that's defined as the modulus of alpha squared. So in this case, alpha is just 3i over 5. And so we plug that in there, the modulus of 3i over 5, all squared. And in this case, if you take the modulus of this, 3i over 5, is in fact just 3 over 5. So when we square it, we don't have any I squared turning into -1. We just have plain old 3 over 5 squared. And that, in this case, would give you 9 over 25 as your probability of measuring 0. Now, the point of this slide is to show that this is actually the exact same as what we got for our inner product calculation. This 3i over 5 that we took as alpha is in fact equal to the inner product between 0 and ket psi. So another way of writing this, you could forget all about the alpha stuff. You don't have to write it in this form. If I had literally just told you, hey, this is the inner product of 0 and psi, what's the probability of measuring 0? You can just take the modulus of that whole thing and square it, and you'll still get the probability of measuring 0. So stating this a little bit more generally, the probability of measuring 0, as we said, is defined as the modulus of alpha squared. But by the definition of inner product, that's actually just the same as the modulus of the inner product of 0 and psi all squared. You could do a similar thing for the probability of measuring 1, which is the modulus of beta squared. In this case, though, it's going to be the modulus of the inner product of 1 and psi. So in general, the probability of measuring something, x, is just going to be the modulus of the inner product of x and psi all squared. So that's just a handy pattern you can try and remember. But as we saw here, it's not too difficult to derive on your own if you would like as well. So that is actually it. That's all we have for the optional content this week, is just to point out this connection, I guess, between inner product and measurement. Turns out inner product and measurement are very tightly related. So keep this in mind. It will come up again in the second semester, and I'm sure we'll remind you about it, but we'll just introduce it a little bit for now. That's all I have for the optional content. So I guess I'll just ask one more time. Does anybody have any questions they would like me to go over before we sign off for the night? Okay, oh, there we go. So the question is, if we calculated the probability of 0, would the probability of 1 just be 1 minus the probability of 0? Yes, exactly. So by the definition of probability, your probabilities always have to add to 1. And so you could calculate the probability of measuring 1 as just 1 minus the probability of measuring 0. That is totally valid. Okay, anybody else have questions? All right. If not, then I guess I will sign off here and wrap things up. I guess just one final note. This lab to me is where we really start getting a feel for the mathematics of quantum computing. A lot of the types of problems we did here is what we're going to see a lot more of in semester 2. And crucially, this is very close to what you actually program in IBM to operate the quantum computer. So we're getting close now, I promise, to actual quantum computations, to the whole point of this course. And so hopefully that serves as some excitement, at least, when you go into this week's homework. Good luck with that. And as always, feel free to go and post on Piazza if you have any questions. Thanks so much for sticking it out right until the end of the optional content. We'll see you next week, and good luck again with the homework. Bye.